what I'd like to do now is talk about a concept that's kind of dual to mobility. Okay, so mobility is the idea of in what ways can this mechanism move? Okay, can this robot move? Okay, so let's talk about the other concept. How can we immobilize an object? Okay, so the easiest example is grasping. Okay, so I showed you this on the first day of class. When we grasp an object, right, I grasp it. So if you tell me just use 3 fingers, grasp it. Okay. Okay. Now, if you ask a robot to grasp this, okay, you'll think about it for a while. Look at it, you know. Say, let's put the fingers here, here, here. Okay. And sometimes it falls out. Okay. So that was a bad grasp. Okay. So even for the simplest tasks, you have to tell the robot exactly what to do. Okay. Where to place the fingers. Okay? Or how many fingers to use. Okay. But here the idea is we want to immobilize this object, make this object stationary. Okay. All right, so that's what we're going to talk about today. So we need to give it a topic here. So let's call it grasping. Okay, so the 2 main concepts we'll be using are the notion of form closure and force closure. So let's write it, form and force closure. Okay. All right, let's start off with a sort of a simple, well, not simple, but a motivating, intuitive example. Okay. All right, so motivating example. Okay, so suppose you have a picture, square picture. Okay, and we're going to place the picture on the wall. Okay, but rather than use a single nail, we're going to use 4 nails or 4 pins. Okay, and we're going to place the pins. Okay, so let's draw this. So let's say in the first case we place the pins symmetrically, like that. Okay. All right, so somebody places the pins like that. Okay. Somebody else looks at it and says, well, that's a silly way to frame a picture. Okay. And says this, and he claims that this is a better way. Okay. Okay. So these are sort of 4. It's a pin. Okay. And these are all pins. Okay. Okay. So these pins have no friction. Okay. So there's small metal pins. Okay. So these pins are, let's write it down. So frictionless point contacts. Okay, so we have 4 of them. Okay, all right. So we have this like a picture frame that we just put on the wall. Put a pin here, 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 here. Versus in this case, we put the pins at the corners. Okay. All right. So what's better? What's more? All right, so which is better? Okay. All right, so let's have another great experiment in democracy. Okay, so how many people think this is better? Okay, so hopefully we'll have more voter participation this time. So let's see some votes here. Okay, so it looks like roughly maybe about 1/4 of the class. Okay, how many think this is better? Okay, this looks like roughly about maybe slightly more. Okay, So that means we still don't have 50% voter participation. Okay, but that's okay. We'll get a definite answer by the end of class today, which is better. Okay, but turns out this is better. Okay, this is better. I'm not going to tell you why now. Okay, we'll get to that at the end. All right. Okay, here's another example. Okay, so suppose I have some triangular object. Okay, and this time I'm going to use my fingers. Okay, use my fingers to grasp this object. So in the first case, I put my finger, say, here. Okay, so my fingers have friction. Okay, and in the second case, I decide to grasp the object that way. Okay, so these are point contacts with friction. Okay, so you can imagine these pins, but maybe I put some glue on the pins. Okay, so it's kind of sticky. All right, okay, so let me ask the same question here. Which is better? Okay. All right, should we try a vote again? Okay, how many vote for this? Okay, looks like about 15 or so. How many vote for this? Okay, this time we seem to have a larger majority here. Okay. All right. Well, democracy works. The majority, we have to go with the majority. So, in fact, this is better. Okay. And we'll see why this is better next class. Okay, not this class. All right. So these are very practical questions that we're going to be addressing. All right, so what have these very practical problems got to do with those words form and forced closure? Those are probably words that you've probably are seeing for the first time. Okay, so let me explain to you what they are. So form closure, okay, roughly the idea is that an object is completely immobilized, okay? Is immobilized. Okay, immobilized means it can't move, it's stationary, by a set of, okay, so we'll just worry about point contacts now. Okay, by a set of point contacts. Okay, so it's that situation over there. Okay, so if we use 4 pins, the picture can't move. Okay, so forced closure is related but slightly different. Okay. So in the case of forced closure, an object cannot move. It's completely immobilized. In the case of forced closure, what it means is that, so let's think of these as fingers. Okay. So I guess stick your finger. Okay, so fingers, okay, can apply a force can apply forces, okay, such that it can resist any external force applied to the same object. Okay. Okay. Any external forces on object. Okay, so it's like this idea here. So suppose gravity is acting this way. Okay, that means I have my fingers here. Okay, now if I squeeze the object hard, it's not going to fall, right? But if I just hold it very lightly, the object can fall, right? So, here's the object, right? If I squeeze it hard, it's not going to fall. Okay, but if I just touch it very lightly, the forces might not be enough and it might just slip. Okay, so the idea is that I can immobilize it by applying strong forces, strong enough forces. Okay, whereas form closure, the object is always stationary. Okay, all right. Okay, so so is friction good or bad here? Friction good or bad? I think it's good, right? That's why our fingers have some friction. Okay. All right, so friction helps. Okay, so how much does it help? We need to answer that question. So we have to look at contact models, okay, for friction. Okay, so those of you who have taken dynamics probably are quite familiar with this. Those of you who haven't, you have to sort of go back maybe toward freshman physics or maybe high school physics, where you studied Coulomb forces and friction. Okay, so here's a refresher for that. So suppose I have some plane. And let's say that's a finger. Okay, so it's a very sharp finger, point contact. Okay. All right. So it's pressing against the table, for example. Let's get angled, right? So it's pressing against the table like this. Okay. So that means there's a force being applied that way. Okay, let me call this force F. Okay. And now, if there's friction here at this contact, then the Coulomb model for friction says that what? The friction force is proportional to the normal force. Okay, so I can decompose this force F into a normal component, Fn, and a tangential component, Ft. Okay, so this is 90 degrees. So F is equal to Fn plus Ft. Okay, and then the Coulomb friction is given by the normal force times times the normal force mu F of n. Okay, and this friction force is in the direction opposite to the force being applied. Okay, it resists the motion. Okay, so it looks like this. Okay, so let's just complete the triangle here. Make it look nicer. Okay, so when does slip occur? When do we have sliding? When do we have sliding? Sliding occurs if this friction force is bigger than this tangential force. Okay, so slipping occurs when the tangential force, the component, is less than mu times Fn, the normal force. Oh, sorry, I got the other way. That's what happens, right? Okay, so mu is this the Coulomb friction coefficient. Okay, so friction is a very complicated thing. Okay, there's static friction, there's rolling, all kinds of different friction models. We're just going to use a very simple Coulomb friction. Okay, it's good enough for our purposes. Okay. Let me call these angles alpha and beta. Okay, so I have two angles, alpha and beta. Okay, so it's pretty clear that this is the same as saying that the angle beta is bigger than alpha. Okay, so equivalently, okay, so slip, when slip occurs, that's the same as saying that alpha is less than beta. Okay, all right. So what is alpha here? Well, turns out alpha is just tangent inverse of mu. Okay, and that should be clear from just straightforward trigonometry. All right, so okay, so from now on, when we talk about friction, we're not going to use the Coulomb friction coefficient mu. Okay, rather we want to keep doing geometric. So we're going to talk about friction in terms of a friction cone. Okay, so friction cone. Okay, so if we have some object, and here's our finger. Okay, so at this contact, we're going to have a cone. Okay, so this angle here, so let's make sure it's, so this angle here will be 2 alpha. Okay, so this is our friction cone. Now, if the force being applied at this point, okay, is inside the cone, okay, then there's no slip. If the force being applied it falls outside the cone, then slipping occurs. Okay, and that should be clear from this picture. Okay, so if force is outside the cone, outside this friction cone, then we have slip. Okay, all right. So from now on, friction cone rather than the Coulomb friction coefficient mu. All right, so we're going to deal with two types of contact. Okay, and these are, you've already seen examples of these. Okay, so the first is the point contact with no friction. We'll just call that the frictionless point contact. Okay, so frictionless point contact. Okay, so here the cone is 0. The friction cone angle is 0. Okay, so that means alpha equals 0. Okay, alpha equals 0, or equivalently mu equals 0. Okay, so that means what? Forces that can be applied must always be normal to the surface. Okay, so only normal forces can be applied. Can be applied. Okay, so that's frictionless point contact. So the other case is now the point contact with friction. Okay, so let's write that here. So we have, same case, point contact with friction. Okay, so here forces have to be inside the friction cone in order for there to be no slip. Okay. Okay. Now our fingers, so these are, okay. Okay, so consider planar case today. Okay, so we'll look at the spatial case later. Okay, but our fingers, okay, when we grasp an object like this, we have, okay, we have obviously friction at the contact. Okay, so in 3 dimensions, our fingers have friction that applies in both the x and y directions. But there's also another degree of dimension in which friction applies, and that is this direction. Okay, so if there's enough friction, we can, right, cause the object to rotate a little bit, as long as we're inside the friction cone in this direction. Okay, so we'll cover that when we get to the spatial case. All right.